Hello everyone, welcome to 10-Minute Physiology. In today's video we're going to talk about the physics behind vision, so with that let's give it a go. So I'd like to begin by first talking about the electromagnetic spectrum. So the electromagnetic spectrum looks something like this, and it describes the spectrum of wavelengths that light can have. So it's important to realize that the wavelength of light and energy are going to be related to each other, and it can be described by this equation here. So this right here tells you how to calculate the energy of a specific light wave. So the energy of light is going to be equal to Planck's constant times the frequency. And the frequency is going to be equal to the speed of light divided by the wavelength. So the main thing that you have to note from this equation is that energy is going to be directly proportional to the frequency of light, and energy is going to be indirectly proportional to the wavelength. So when the wavelength of light increases, this causes the frequency to decrease and therefore the energy to decrease. And when the wavelength of light decreases, this causes the frequency to increase and the energy to increase as well. So the most important part of the electromagnetic spectrum is going to be the visible light spectrum. So the visible light spectrum is going to be spanning from 400 to 750 nanometers, and this is what our eyes are able to perceive. Now, let's talk about how light is going to travel through the eye. So if you were to trace the pathway of light through the eye, the first place that it would go through is the cornea. So the cornea is going to be the outer clear covering of the eye, and it's basically going to be made up of epithelial cells. And this is actually where the greatest degree of refraction or bending is going to occur. So after this occurs with the cornea, what happens is that the light will pass through the anterior chamber, and then through the pupil, and then after that it will travel through the lens, and then into the vitreous humor, which is fluid that fills the vitreous body, and then it will hit the retina, where the signal is transduced into the optic nerve. So before we can talk about how our eyes are going to perceive light, we have to talk about a specific physics quality called refraction. So what is refraction? So imagine you have a flashlight and you're shining this flashlight in a vacuum. Now when you shine the light beam in a vacuum, you can measure the speed of light. And when you do so, you see that the speed of light, or the speed of the light beam, is going to be equal to 3 times 10 to the 8th meters per second. And this is the speed of light in a vacuum. But if you were to shine the same flashlight in, let's just say, a room full of oxygen, the speed of the light beam would actually be a little bit slower. And the reason why is because when light travels through media, it will slow down when it's compared to light traveling through a vacuum. So when light is in a medium other than a vacuum, it slows down. So what happens to the light beam when it slows down? Well, in order to understand this, let's take a look at an example. So let's just say you have a lens, and this lens is made out of glass. And what we have here is that the lens is inside a vacuum. So when we have this lens in the vacuum and you shine light beams through it, what you would see is something like this. So when the light beams pass through the lens, the light beams are going to slow down. And as a result of this, the light is going to bend. So when light slows down, it actually bends. And this action of bending is what we call refraction. So with that, we can have two different types of lenses. So this lens right here is something called a converging or convex lens. So converging or convex lens focuses the light rays onto a single point, as we see right here. And this is the type of lens that we have in our eye. The other type of lens is a diverging lens. And it's called a diverging lens because it causes the light rays to spread out like this. So diverging lenses are also called concave lenses. So now that we know what refraction is, in that it's the bending of light, we can now talk about how it's going to bend, and we can actually calculate how much the light is going to bend, passes from one medium into another. But in order to calculate how much light is going to bend, you have to know a specific quantity called the index of refraction. So the index of refraction is going to be a characteristic value of a specific substance. So it differs depending upon the substance or medium. And it basically describes how much light rays will slow down when it passes through that object. You can calculate the index of refraction for a specific substance by using this equation, where you have the speed of light in the numerator in the vacuum and the speed of light through the media in the denominator. And when you calculate this, you can get the index of refraction for a specific substance. Now you can use this value in order to calculate how much light will bend when it passes from one media into another media. And the way we can do that is through Snell's law. So this right here is Snell's law, and it's basically used to calculate how much light will bend when it passes from one medium into another medium. And we're going to give an example as to how we can use this law in a second. So in order to understand how Snell's law works, let's just say you have this scenario. So on this side of the blue line, you have air, and on this side of the blue line, you have water. So this is the surface of water, and this is air. So what we're going to do is we're going to shine a light at a specific angle and see how much that light bends when it enters into the water. Now before we can do that, we have to identify a specific line called the normal. So the normal is how we're going to define our angles. So if you were to take a light beam and shine it at this angle, theta 1, respective to the normal, how much would the light bend when it enters into the water? Well, in order to answer that, we have to know a few things. So the first thing we have to know is we have to know the index of refraction for air and the angle that the light is entering into the water respective to the normal. And what we see here is that the index of refraction for air we can just assume is around 1, and the angle in which light enters respective to the normal is 30 degrees. Now, in order to see how much light is going to bend when it enters into the water, we have to know the index of refraction for water. And the index of refraction for water is 1.33. So now what we can do is we can use Snell's law in order to calculate the angle at which the light will be refracted in the water. And when you do that, you would get a value of 22.08 degrees. So what we see here is that when light entered into the water, the light bent toward the normal. So now what we're going to do is we're going to talk about something called focal power. So focal power basically describes how well a lens can focus light. And we can do that using this equation here. So this right here is the focal power. And the other main thing that you have to look at here is this in the denominator. So this is the radius of curvature. So the radius of curvature is basically going to be a very important quality, and it's going to be something like this. So imagine you have a lens, and if you were to make this lens into a circle like this, so if you were to take these two ends and trace a circle, what you would get is something called the radius of curvature. So the radius of curvature basically helps you to describe how curved your lens is. So if you have a smaller radius, you get a larger focusing power. A larger radius gives you a smaller focusing power. So in this video, we talked about a few things. We talked about the visible spectrum, how light passes through the eye. We also talked about the speed of light and how it varies through different media. We talked about the two types of lenses. We talked about Snell's law, and we gave a short introduction into focal power. So I hope this video helped you understand these topics, and I hope to see you in the next one. Thanks for watching, and I hope to see you next time.